Okay, the other problem was that you were given this diester, and it's supposed to be converted into a ketone. And in your ketone, realize there is a benzene ring, it's a C double bond O, and then there are 4 carbons. Realize you started with a diester, you have nothing that looks like an ester in your product. So you can perhaps envision this will go through what I was talking about in class earlier today, that it will go through a beta keto ester type of a moiety, which essentially will lose the ester group, the entire ester group, and perhaps with the other ester group, what's remaining, you can carry out some kind of a reduction or something to get your product. Let's see if we can, what we can do with this. So right now you have only 1, 2, and 3. We have 3 carbons total. So let's see what would happen if I treat this with, because the first step you can think of is deprotonation, so this must be treated with some kind of a base. That should be your first step, and treated with kind of like a chain elongation that needs to be done. Now realize in this case, realize what we have in the product side. I have a benzene ring with a C double bond O. So the easiest one can think of is that if this aliphatic part, if that can be reduced to perhaps this part here, then you can always use benzene as is through a Friedel-Crafts acylation, and you can carry out the reaction. So essentially my aim right now is that if somehow I can convert the given molecule into something like an acid chloride like this. Now you know the acid chloride can be generated using carboxylic acid. The carboxylic acid can be generated using, in this particular case, maybe just acid and heat. So you have 2 carbons already, and this one has 1, 2, 3, 4, and 5. If this guy has to be left as CO2 and ethanol, then you still need 1, 2, and 3 carbons more. So I'm going to treat this with sodium hydride and a 3-carbon bromine. Let's begin with that and see where we go with it. So of course the deprotonation will take place, and past the deprotonation, essentially the negative is going to attack right here, bromine is going to leave. You're going to end up with COOET on one side and the other in a symmetrical manner, so from the malonic acid, and we have 3 carbon chain that has gotten added to the alpha position. All you got to do is treat it with acid and heat it. So in that process, one of the ester groups is going to cleave off and will give you the ester of pentanoic acid. So you'll first get the ester. Treat that with, so carry out a hydrolysis essentially. And you can do an acid hydrolysis and base hydrolysis. Actually, depending on the concentration of the acid, you might be able to get rid of that ethanol like completely. And you get OH. That can be converted to acid chloride using thionyl chloride. Benzene is your solvent. And that can be treated with benzene and AlCl3, and you have your Friedel-Crafts acylated product. That is what we sought to generate. Okay, in this particular problem, you're given a ketone, a cyclic ketone at that, and you're converting it into a tertiary alcohol. So the fact that there's a tertiary alcohol probably should tell you that there'll be a Grignard reagent involved in this part. Let's just mark that. In this part, there should be some kind of Grignard reagent. Also realize that there are substitutions that are ongoing at the alpha position and the beta position. So maybe some kind of alpha beta unsaturated ketone would be generated. So let's say the first step is, and I think I did part of it, like a kind of this type of a reaction, but not quite exactly this. This is going to give you the alpha brominated compound. This can be subjected to treatment with T-butoxide, which is a great base, and that will essentially take away the beta hydrogens. So these are going to be O negative. So this is going to go away, electrons will move, Br will go away, and you will end up with essentially alpha beta unsaturated compound that can be treated with, notice you need an ethyl group here, so I'm going to just treat it with ethyl 2-CuLi. So ethyl lithium cuprate is what I'm going to treat it with. Follow it with hydrolysis so that you end up adding an ethyl group at the beta position. Treat this with LDA because LDA will take away protons from the alpha position, and treat it with methyl bromide, and that will give you this. You can choose to do this first and then carry out. It's just that the steric hindrance will probably not allow the reaction to go to completion. Now that you have both the substitutions, all you got to do is treat this with, you need a phenyl group, so let's treat it with phenyl magnesium bromide. That should be our first step, and follow it with hydrolysis, and that will give you the tertiary alcohol that you were seeking. Okay, the last one is that you have beta keto ester. So this is alpha, that's beta, again beta keto ester, and we are converting it to an imine. Now let's do a retro just the same way we have been doing. The fact that it is an imine should tell you that if you cleave right here, let's maybe change the color. If you cleave right here, essentially you can generate 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, plus methylamine CH3 NH2. So essentially, if I can get this ketone from that beta keto system, I would be able to get what I need. Again, realize my starting material has an ester. On the other hand, my product does not. So you have to get rid of that ester. What does that mean? That means that you would be at some point of time generating or treat it with an acid and heat it so that you can get rid of that entire ester group. So let's put that phenyl group because that's what is lacking. So envision 1, 2, 3. So I'm going to treat this with first step, of course, sodium hydride or NaOMe, some kind of a base, strong base at that. And I'm going to treat that with an alkyl halide. Okay, so I have carbon number 1. This is the carbon that is right here, the alpha carbon. That's going to go through deprotonation, and it's going to attack. Reaction will occur right here. It contains 2 carbons past that, and then the ring. So it contains 2 carbons right here, and then the phenyl ring. And so what you're going to end up with is COOET, carbon, carbon, and then a ring. You're going to subject that to hydrolysis, H3O+, follow it with heat, and you're going to lose the COOET part to hydrolysis and decomposition, and you will generate your ketone. That, when treated with methylamine, is going to attack right here, since it's occurring in presence of water, the OH2 will leave and the double bond NH will form, and your desired product is generated. So you can realize that in this particular chapter specifically, since the nature of the products is a little bit complicated, it helps sometimes to just carry out a little bit of a retro analysis as to how you could have achieved that structure. So if it's an imine, for example, in this case, it could have been derived from the corresponding ketone and the methylamine. Likewise, if compare the structure of the starting material and one of the intermediates, and if you don't see an ester, how could you have lost that? And one of the very good methods of that would be if you have a beta keto system, essentially treatment with acid and heat is going to make you lose that particular ester in the form of CO2 ethanol. So hopefully this helped, and if not, well, you know where to email me or the office hours. So see you Wednesday. Bye bye and good luck.